Now that we have our focal points, we can start to calculate our image distances. We'll start with the first one. Before we do that, let's just rewrite this equation. 1 over object distance plus 1 over image distance is equal to 1 over focal length. And I want to write this in terms of my image distance. So image distance is going to be equal to object distance times the focal point or focal length divided by object distance minus the focal length. So this will simplify our formulas just a little bit. We don't have to keep using the same, solving for everything. So let's look at our distance, image distance for the glass. That's going to be equal to our 25 centimeters. That's our starting out distance from the lens times the focal length, which is 11.538, divide that by 25 centimeters minus 11.538 centimeters, and that gives me a distance of 21.429 centimeters. Now I can calculate the magnification. Magnification is just negative image distance over object distance. Funny enough, it's the same as our spherical mirrors. And so we have negative 21.429 centimeters divided by 25 centimeters. And that gives us a magnification of negative 0.857, about 86%. So now I have the image for the glass. That image becomes the object for the quartz. So my object distance for quartz is equal to my distance between the lenses, ds1, that's 24 centimeters, minus the image distance of the glass, so that's 24 centimeters, minus 21.429 centimeters, and that gives me 2.571 centimeters. Now this means that this is with relation to the axis of the second lens. And depending on what we do, our image could be further out from the object, and it could be behind, but this formula will always work if you follow this. The distance between the lenses minus the image, this will always work. So you don't have to change this equation for double convex or double concave, because we keep everything in terms of positive and negative numbers. So we'll be able to just use this equation, these equations in the form, just putting in positive and negative numbers. Now I can calculate the image for the quartz, and that's just going to be equal to the 2.571 centimeters times our focal point for the quartz was negative 9.662 centimeters, and divide that by 2.571 centimeters minus a negative 9.662 centimeters. Remember to keep that focal length correct with our sign here. So we have minus, and then we're going to have a minus a focal length. And that distance will give us negative 2.031, and that's centimeters. Our magnification is just going to be our image distance, which is negative 2.031 centimeters, divided by our object distance, which is 2.571 centimeters, and that gives us an amplification of 0.79. Positive magnification means that the image and the object are oriented the same way along the horizontal axis. Now I can calculate my object for the diamond, my object distance. And again, that's going to be the distance between the axis of lens 2 and 3 minus the image distance of the quartz, and this is 15 centimeters minus a negative 2.031 centimeters. So notice again, it's the same. You have a minus sign between it, but you have to use the negative of the image distance, and that gives us 17.031 centimeters. And then our image for the diamond is equal to 17.031 centimeters times our focal length of minus 4.225 centimeters divided by 17.031 centimeters minus a negative 4.225 centimeters, and that gives us a distance of negative 3.385 centimeters. Our magnification is equal to negative, well, I'm going to have a negative of a negative, that's a positive. So, I forgot to put the negative up here for this one. So, negative of the negative, so it's negative 3.385 centimeters divided by the 17.031 centimeters, and that gives us a total of 0.199. Our total magnification is just equal to M1, we'll call this M1, M2, M3, M1 times M2 times M3, and that gives us a negative 0.135. So our magnification is very small, and the orientation is that the image, the final image, is on the opposite side of the horizontal axis from the original object.